Everybody was good with the range. These are populations, they first told us, but also these are all for each of the American football teams in the conference. So that's all part of the calculation. You're going to put it in your one-bear stat. On your yellow calculators, make sure your frequency then is blanked out. Sometimes it automatically fills it in with L1 for some reason, so you say L1, L1, and you don't want to do that. Make sure in your yellow calculators that it'll say L1, and then for frequency, this needs to be blank. You need to blank that out. The mean in your calculator is your X bar. The standard deviation in your calculator is this guy, the sigma X. To get back to your variance in your calculator, you got to work at the reverse that we did on your table. In your table, we found in the table that we worked out, we found your variance, then we took the square root. You have to work backwards. You have to go to theirs. You have to go to number 5 statistics, come down to the sigma X, and then square it. This will give you your variance. What happens when you square this, you already rounded it off. You changed that number. So you'll never get back to your true variance. You'll get back to one close enough, but it may not be your true variance. Okay, again, for all U.S. presidents, here's the population since 1952. All right, so put it in your calc again, give you the range. The mean appears as your X bar, and use population because this was for population. Your standard deviation is your population one, and again, go into your VARs and give me your variance. Can we do that? If anybody not able to do that, I can come over and work with you. No? Okay, good. Most of this course is standard deviations and variances.
How do you determine the difference between sample and population?
Well, first of all, your directions did, because it said for the population data set. But what you say of all presidents' population, for each of the ones in this, meaning for everyone, when they include all population. If they said for some, then I'm talking sample. Okay, now, they did tell you in the thing population, which is a good thing because since 1952, you could say, well, this is a sample of all the presidents, but they kind of qualified it. So they did tell you again, because this would be a dicky one. You could go with sample if you said these are the only part of the president. So, but they did kind of tell you ahead of time, which is why they would. Find a range and see, now they told us this was a sample for shoppers at a clothing outlet, and you can imagine that it would be a sample because wouldn't there be many more? Okay, you're looking for ages, and put it in our calcs. Again, X bar is your mean, and your sample standard deviation in your calculator is your SX. Sample X, remember sample for X. Your mean always comes out whether it's population or sample. We do a little lab later in the year, like as we get into this a little bit more, and you'll see that your sample and your population mean always kind of gravitate together, but not your standard deviation, because we saw it in your table. We subtract n minus 1 for your sample standard deviation. Can everybody do this? Good? Easy? Okay. Just so that you get an understanding of this. This was a nice one just to eyeball this. We said rule of thumb with standard deviation. The closer your data set, the smaller the deviance from the mean, right? So the smaller the standard deviation. So this data set is a little bit closer to the mean. This data set is a little bit spread out. Look where it went to. There's the 20s, there's the 18s, there's the 20s and the 12s. This one didn't have a 20 or a 12. So this one was a little closer to the mean. So this one has to get the smaller standard deviation, which in this case is 16. This one's more spread out, more variable in here. So that gets the 24. I'm going to skip 19 and then come back to it, just because we're on the mode of which one looks better. Again, by eyeballing your data sets, which one is the closest together of your data sets, the least variable? 3. So that has to be the smallest standard deviation. Which data set is the most spread apart? 2. That one is the greatest standard deviation. And then had you do another one. I had to do another one. And the same thing in here. You can kind of see this one's not using any 10s or 14s. This one used 2. This one only used 1. So do you kind of see the further away from the mean? Further away from the mean means you have a greater standard deviation. So this guy has to have the smallest standard deviation, the least. This guy has to have the greatest standard deviation, the most. Okay, and to get back to 19, this was a really good thinking problem. We said standard deviation is how much it deviates off the mean. So if you have both of your companies are the same mean for their starting salary, 31,000, 31,000. One has a standard deviation of 5,000, so it's going out, spread out a lot more. One has a standard deviation of 1,000, so 32,000 would be one away from the mean. 33,000 would be 2 away from the mean. But for the guy with the 5,000, the 33 would be real close to the mean, wouldn't it? Real close to the average. So if you wanted 33,000, wouldn't you be closer to the mean for somebody that has a 5,000 standard deviation? We're going to go more into this today. That's today's lesson, the empirical rule. So maybe this will give you a better understanding with today. So if you didn't get that one, don't worry about that yet. We'll be doing that in a minute. Do you have any other questions about the difference in the variance here? How something deviates off the mean? I need you to get that concept of standard deviation, because we use that throughout the rest of this course. Okay, so let's continue and hit the empirical rule. The empirical rule is really important, and you did this a little bit. You did this a little bit in Algebra 2. Remember the chart that you had on your region? Remember that chart that you looked at in your regions and you figured out standard deviations? I figure out all my standard deviations right off of that. All right. Okay. So we have what we call the empirical rule. In Algebra 2, we kind of defined these a little bit more. This was 68.2% in here, 68.2, because each one of these was 34.1%, more exactly. But we don't do rounds in here a little bit. So their empirical rule says, this is what it says. One standard deviation away from the mean sits most of your data. Look at the way your curve goes. It's like building a mound of sand. So you take all your sand and you build it up in a mound. Where is most of your sand located? In the middle. Good. So this is where most of your data is located. So 68% fall right in here. So when we were talking about the mean and the standard deviation of that people that made 31,000, and one had a standard deviation of 5,000. Remember doing this last year? You put the mean in the middle. Each one of these is one standard deviation above, one standard deviation below. So we added 5,000. You had me for Algebra 2. We definitely did this. Then we added 5,000 again. Then we added 5,000 again. So this is how spread out your salaries are. Going the opposite way, we subtracted 5,000. So for instance, 68% of your salaries are going to fall between these two numbers. In my company, 68% of my employees will make between $26,000 and $36,000 every year. Okay, well, that'll be their annual salary. As opposed to the other guy that said 31,000 in the middle. We always do 1, 2, 3. 0 is the middle, is the mean. If I add, he had a 1,000, 32,000, 33,000, 34,000. Then I go down this way. 30,000, 29,000, 28,000. Most of his employees, 68% of his employees, make between 30,000 and 32,000. That's one standard deviation away from the mean. That's normal. That's what we expect. Remember we talked about the other day, we used the word unusual when it's 2 standard deviations away from the mean. Very unusual when it's 3 standard deviations away from the mean. You don't want to be that far away from the norm, from the mean. So somebody that wants to make 33,000 has a far better chance of making it in here, don't they? Closer to the average. I'm going to pay you closer to what my average employee makes. I'm not going to pay you out here. My average employee doesn't make it out here. That's too far away from my average. I'm going to pay you closer to what my average employee makes. So that's what that number 19 was getting at. Just kind of wanted you to kind of like take a look at where your numbers fell. Wait, I say it again.
The answer was A or B?
The answer is the guy that has the 5,000. Whatever that was. That was B. Okay. Because isn't it more normal for you to occur right in here? In plus or minus 1, most of your values occur here. Look at we get smaller over here, don't we? That's 13% from here to here. This is a real small percent, 2%. This is even tinier, less than 1%. So what happens is you have a better chance of making closer. If you're being hired at my company, would I pay you more than my average employee makes? Would that be good for my employees to see that? I'm going to pay you pretty much what my average employee makes. Where is the average? Higher, right in here. Like when it's 5,000 apart, rather than in here. You're kind of 2 standard deviations above the mean. That means you're pretty good in my company. You're above my normal. You're unusual to be 2 standard deviations above the mean. In covering all your data, plus or minus 2 covers about 95%. About, it's rounded. About 95% of all salaries will be in here. And look how little this is. The plus or minus 3 is 99.7. You still have a little bit left at the edges. Like they have to share 0.3 left at the edges. And it's approximately 100, not totally 100. Okay, well, yeah, because what happens with this, and we're going to talk about this, is this curve goes kind of on and on. So it kind of like fades out. But most of your data, like if you build that hill of sand, your sand is in the middle. That's where most of your things sit. And you need a little bit more here, and you need very, very little on the bottom, right? Very, very little. So that's where your things sit. When we do standard deviations, remember, just like you did in Algebra 2, the 0 is in the middle, the positives are to the right side, the negatives are to the left side. The negative just says you're below the mean. The positive says you're above the mean. When we get to D1, this will look a little bit better. We want to find, in a survey conducted by the National Center for Health Statistics, the sample, here's a sample, always pull this out. The sample height for these women, 64.2 inches, with the sample standard deviation of 2.9. We want to estimate, according to our empirical rule, about what percent of the women's heights fall between 58.4 and 64.2 inches. Now, the best way to do that is off your curve. Everybody draw this curve out with me. We live with this for this entire year. I like this curve on almost everything that you do. Okay, now, the mean goes in the middle. Mean, middle. Mean meaning the mode, smack in the middle. This is called the normal curve. And it's symmetrical. So we take our mean, we put it in the middle. Now, the easiest way to do this is add 2.9 all the way down. So we add 2.9. We get 67.1. We add 2.9 again. We add 2.9 again. And work the opposite way and subtract 2.9. Subtract 2.9 again. And subtract 2.9 again. So our heights pretty much go from 55.5 inches to 72.9 inches. It covers 99.7% of the women in the United States. Most of your women's heights are falling here. Look at the biggest part of my curve. This is the biggest part, 34 and 34%. That's 68% of all women are falling between 61.3 and 6, this is 61.3, and 67.1. And then we go out a little bit more. So if they want to know approximately what percent fall between 58.4, we're going to pull this apart and look for this. We're going to look for 58.4. We're going to look for 64.2. We want to know this right in here. So go back to your empirical chart. This guy right here is 34%. And what's this, 13.5? 13.5? Remember doing this in Algebra 2? Yeah, you do. Add them together. Can't get away with that. You had me. Oh, no, you didn't have me for Algebra 2. You had me for pre-calc. We don't do this in pre-calc. 47.5% of your women's heights will fall between 58.4 and 64.2 inches. Now, I'm going to give you, I should have had it today, but I'm going to give you the chart that you had from your regions. It is the same exact empirical rule, so that you can have one with you. By the end of next week, you won't even need to know that anymore because we convert everything to a z-score. Because what happens when we get a height that falls over here? That's like 59. What do we do with 59? So we have a formula to calculate all of these. But what I want you to see from this is how it's separated, where the symmetry is. The mean goes in the middle. Your standard deviations go block 3 on that side, 3 on this side. They're going to always look the same. Now, estimate how much percent is between 64.2 and 67.1. How much percent, approximately what percent of the women's heights fall between 64.2 and 67.1?
34%.
34%. Good. What percent of the women's heights fall between 58.4 and 70? It's plus or minus how many standard deviations? 95%. Good. It's plus or minus 2 standard deviations, which would be 95% of your women's heights. So do you see how we work this chart? Okay, I need you to get a feel for this. I need you to see where the negative standard deviation is always measured in positive. These gaps we'll call them z-scores. but they're how far away we deviate from the mean. Okay, tomorrow we'll finish this up.